Okay, so we start by defining what's so-called a norm. So if you recall by definition, if we're given a vector space X, then a norm is just an operator that takes an element of X and gives a real number. And this operator shall satisfy three properties. First is the what's so-called triangular inequality, which says that the norm of X plus Y is less than or equal to the norm of X plus the norm of Y. The second one is what's so-called homogeneity. And it says if we have a lambda in K, where lambda is a scalar coming from the field over which X is defined, then we can pull that lambda outside the norm, and we get this. And the third one is saying it's what's so-called positivity, and it says that the norm of X is 0 if and only if X itself is 0. Okay, so as I said, you might be familiar with this notion. However, we want to try to define this to a matrix. But before we do that, let's recall that there are three famous vector norms, or three vital vector norms. The first one is what's so-called the one norm. So if we have an X, say X is a vector written as x1 through xm, then the one norm of X is just the sum of the entries in absolute value. And the second kind of norm we want to define is what's so-called the two norm, which is the norm defined by, which we've seen in the first lecture. It's the norm that is the dot product of the vector with itself, or in other words, it's the square root of the sum of the entries squared in absolute value. Now, there is also a norm of special importance, which is the infinity norm, which is defined to be the maximum over all the entries of the vector that we started with. So these norms play a very important role in the theory, as we shall see in the coming videos. Now, we want to try to define this to a matrix. However, the issue here is that the matrix is it's an m by n vector. So if we want to try to define this to a matrix, there are multiple ways of doing that. Define a norm of a matrix to only depend on the entries of the matrix. However, there's a definition that turned out to be more convenient to work with. So this is what's so-called the induced matrix norm. Okay, so let's see why we're doing that. Well, us introducing the norm for a matrix is a way of defining a measure. We want to define a measure on the matrix, because later on, as we shall see, we'll be talking about algorithms, and we want a way to measure the efficiency and performance of these algorithms. So that's kind of a rough idea why we need this. So now, given that the purpose of this theory is to solve the equation AX equals to B, it's pretty important here to have a norm that is related to the matrix and to vectors at the same time. So hence the definition of an induced norm for a matrix. So if we're given a matrix A, we define the induced norm of A to be the soup over all the ratios of this form. Okay, so it's a way of averaging over here, where we're taking the average over all vectors that are not 0. Well, of course, multiplication here should make sense. Now, if we use homogeneity of a norm, if we use homogeneity of this norm, we can actually get this constant that is the norm of X inside the norm, and we get something like so this is another way of defining the same norm. So if we call this vector V, we see that we'll be taking the soup over all vectors that are of norm 1, because I mean the norm of this thing, again by homogeneity, is just the norm of x over x, which is just 1. Okay, so for that reason, we can rewrite this as the following, as the soup over all v's of norm 1 of ax. Cool. Okay, now that we've defined the matrix norm, we're ready now to discuss some properties of it. So let's do that. Well, first of all, we're gonna discuss like some trivial properties or some easy properties. The first one is, okay, so if you're given a matrix and a vector x, and you're looking at the norm of ax, like you really want to relate this to the norm of a and the norm of x, but you don't actually get a equality, you get an inequality. So you get this inequality. And this is trivial from the very definition of a matrix norm, because, I mean, take the matrix norm, which we define to be the soup over all y's not being 0 of ay over y. And now, since this is a soup over all x's that are not 0, then this should be bigger than or equal the particular element ax over x when we take y to be x. So we get this inequality as a result. Now, the other nice property of this norm is that if you're multiplying two matrices, A and B, so you really want to relate this to the norms A and B. So what you do is that, so also you don't get an equality, but you get an inequality. And this is kind of a consequence of the property 1. So let's see why. Well, if you start by the definition of the norm of AB, you will see that this is the soup, and we can take the norm, we can take the soup over all the x's of norm 1 of ABX. Here we don't need to divide by the norm of x, because again we're taking the norm to be 1, and that's the equivalent definition that we've done here. And oops, this should be a v. And then if you look at this, like this one is just a vector, right? Bx is just a vector. So if you call it v and we use property 1 on A and B, we can separate these, or we can get an inequality as such. Like we're applying property 1 to A and V. So the norm of AV will be less than the norm of A times the norm of V, but V is here Bx. And we apply the property again. And we have, this is less than the norm of A times the norm of B times the norm of X. But X here is of norm 1, so we can just replace that by 1. We can remove this. And since this is a constant independent of X, we can just get rid of the soup thing. And we get the inequality that is desired. Okay, and now we're ready to explore more properties of matrix norm. So if you stare at this definition of the induced matrix norm, you see that we can define what's so-called a 2 induced norm by just taking the 2 norms over here. And similarly for the 1 norm and the infinity norm. However, the issue with these norms is that like they're very hard to compute. Like imagine you sitting and trying to calculate the supremum over like infinitely many vectors, and that is very hard to do, right? So what we're gonna do is that we're gonna try to define some equivalent definitions of the 1 and the infinity norms, by the following theorem. So let us try to do that. So this theorem says the following. Okay, if you're given a matrix A, say that is written as Aij, then the first part of the theorem says that the one norm of A is the maximum colon sum, let me say maximum absolute colon sum of A. And what that means is that you consider, like, you take the maximum over all J's indexing the columns, and you sum each column, you sum the entries of each column over I. This is the first part of the statement. And the second part of the theorem is the infinity norm of A is just the maximum absolute row sum of A. And that's the maximum over all rows where we sum the row entry over J. So over here, we're fixing J, we're fixing a column and considering its sum, and then we get a number. And then we do that for every J and we take the maximum over these. So why is this important in the first place? Well, just imagine, like, we've descended from calculating the supremum over infinitely many vectors to just summing the entries of the row, like the entries of the rows and the columns, and just taking the maximums of the sums, right? Like, this is tremendously easier, right? So let us prove this theorem. The proof isn't that bad, so let us do the proof.